All right, so next section. Let me share the whole thing because I'm going to use my calculator. And here we go. All right, so this first page is a review. I'd like you to hit pause and give it a try. So there's 3 questions dealing with what we did yesterday. Don't skip this part. You know, I kept stressing that in the beginning of the year. We haven't sort of done this very much with the last few units, but it's time again. So, you know, make sure you try these. So hit pause. I'm about to do the answers. All right, so here goes. All right, so write the equilibrium constant expression. So the equilibrium constant expression is you do the products, P4O10, over the reactants, P4 and O2 to the 5th, but you leave out the pure solids. So this thing is going to be 1 over the molarity of O2 to the 5th power. And then when we do the Kc or the Kp expression, which is you just do gases. So once again, we don't have any products. So products over the reactant, which is O2 to the 5th power. Remember, no brackets when you do the Kp. Don't mark it wrong if you do brackets. Oops. Second one. So once again, we're writing the Kc this time. So the Kc expression is Hi to the squared over H2. So that's how you start all equilibrium problems. You're going to see what we do tomorrow. We're going to start each time by writing the equilibrium expression, and what we do today, you'll see too. For the system, Hi is in equilibrium with 1/2 H2 and 1/2 I2. So notice it's this same equation, but they have reversed it. Remember, when you reverse it, it's 1 over. And they also divided by 2, or I like to do it as multiplied by. So they multiplied by 1/2. And the reason I like to multiply it by, it's, well, you know, what you multiply it by becomes a coefficient, not what you divide by. And so it's 1 over 55. And it is 1 over 55 to the 1/2 power. So we're going to reverse it. So we inverse it, and we're going to multiply it by 1/2. Looks like I'm doing all right. Yep. Yeah. All right. So it is 1 divided by 55. I have a caret, so to the 0.5, or you can take the square root, 0.135. So the K value of the reverse reaction, where you're multiplying by 1/2, is 0.135. And now we're doing the same thing. So we have this third reaction. They give us a temperature each time, you'll see. And the reason for that is K value, just like the K value when we were doing rate constants, depends on temperature. So if you change the temperature, it actually changes the K value, or there's a good chance that it changes the K value. All right, so we're going to combine these two, and then we're going to multiply. Remember, it's not adding, but multiplying whatever happens to the K values. I have CO2 on the left-hand side. I have it on the left or the right-hand side. It's on the right-hand side. So the second reaction is good. I have CO though, C capital O. That's also on the right side. But then I have water on the left and water's on the right. So I have to reverse the first reaction. Which means it's 1 over 67. But the second reaction is staying. So this one is staying 490. Now you can still cancel, so you can see I have COO, COO, and I have the right reaction. And then, like I said, with these, we multiply. We don't add, we multiply. So 1 divided by 67, and we got 0.0149. And then we didn't do anything to that one. And so we're multiplying 2 together, and we get 7.31. So our K for our combination of those two is 7.31. All right, so that's the review. Okay, so here's what we're learning today. So we're going to learn something called an ice chart today, an ice chart. And recall that equilibrium concentrations are not constant. They depend on the initial concentration. And so there is a lab activity that we have done, or we're going to do, I'm not sure which yet, as I'm making this. I may have you do the reaction, that lab experiment after we do this. I might have you do it before. But the K value is a constant. So the K value is a constant. So though the equilibrium concentrations can be different, the K is a constant. So that products over reactants coefficients become exponents. You can see they have done that over here. So here's our reaction. Here's our K expression. So then they're starting with different initial concentrations. You can see we varied them, which then varied, the equilibrium concentrations. But when you plug the equilibrium concentrations into the K expression, you can see you get the same value. So though you start with different materials, you always end up in the same place in terms of K. All right, here goes. Let's just jump in and try this. So we have CO. I'm just going to rewrite it so I can do my ice chart. All right, sometimes they add an R and they call these rice charts. I don't do that because I didn't learn it that way, but if you like it, go for it. So the ice goes like so, and they stand for the initial concentrations. So what's happening in the beginning, the change that occurs, and this change is done in terms of X, you're going to see, and it follows the stoichiometry. And then this is the equilibrium concentrations. So the difference between the initial and the equilibrium is equilibrium is at equilibrium. The initial can be literally any values. All right, so they give you a temperature, as I said, but we don't need it yet, although the temperature is not changing. So this reaction mixture initially contains a molarity of 0.5. Remember, this has to be molarity. Brackets means molarity. And 1, which means there's none of this to start with. All right, so now, if tomorrow, or actually in a few minutes, we're going to figure out how to deal with which direction. And then tomorrow, we're going to vary how these initial conditions start. But for today, one side is going to have nothing. So in this case, this right-hand side here, we don't have any, which means, does this reaction proceed by going from left to right, or does it start by going from right to left? Well, it has to go from left to right. Why? Well, because you don't have any CH3OH, so it can't possibly go to the left initially. So I now know that this reaction proceeds from left to right. Now here's why that matters. The concentration of CO is going to go down. Down by how much? Don't know yet. But whatever it is, it's going to be 1x because of the stoichiometry. So there's a 1 understood to be in front of CO. So there's a 1 understood to be in front of our x. But when we do hydrogen, it's actually minus 2x because, again, the stoichiometry. So for every 1 mole of CO you lose 2 moles of H2. So that's what that means. And then over here, we're not going to lose these, but we're going to get plus, and it's going to be whatever x is, again, due to the stoichiometry. So then the concentration at equilibrium of CO is 0.5, its initial concentration, minus x, the change. This would be 1.0 minus 2 times whatever x is. And this is 0 plus x. So I usually just write x. It's whatever x is. All right, so now from there, the best thing you could do for yourself is get in the habit of writing the equilibrium expression. Sometimes you will be explicitly asked to write the equilibrium expression. Sometimes you will not be asked explicitly to write it, but you always get a point for it when you do have to write it on the AP test. So I think it's a good habit to start there. All right, so now from this, so I wrote the ice chart and the equilibrium expression. We're going to start every equilibrium problem the same. And that's going to be true now for the next unit on acids and bases and pH and all the equilibriums associated with Ka and Kb, acid base. We're also going to do that with Ksb, solubility constant equilibriums. So that's why I say get in the habit now. All right, so now where we go from there is going to vary depending on what we're given. So the additional piece of information we're given. So we have the initial. It says at equilibrium. So now we're at this stage, the equilibrium stage. The CO concentration equals 0.15. Now I like to circle right there showing me which equilibrium concentration is correct, because I have 0.5 minus x, which is what equilibrium equals, but I just said in the problem that it also equals 0.15. So now I know that 0.15 minus x equals, or 0.5 minus x equals 0.15. So that x equals 0.35. So now this one at equilibrium is 0.35 because it's x, and this one is 1 minus 2 times x. So 2 times 0.35 is 0.7, 1 minus 0.7, and we got, come on, there we go. So this is 0.3. So now I have the three concentrations, because the next one says, what is the value of the equilibrium constant? So now I have the Kc expression, so it's equal to 0.35 over 0.15 times 0.30. Don't forget the square. 0.35 divided by 0.15 divided by 0.3 squared. And we got 25.9. Now, I didn't mention this yesterday, and I should have, but the K values are unitless, because you can see how they can vary depending on whether one is squared, one's cubed, they're all to the first power. So the general convention with Ks are the units are left off. So for once, you don't have to worry about units, which is unique. All right, so the next one's basically the same. I'm gonna do this one too. Let me move me over here so it's not in my way. All right, so next one. So you're gonna see now that the start to these are gonna start to become very repetitive. Not yet, it's only our second one, but we're gonna do the same thing each time. We're gonna write the equation, we're gonna do the ice chart, and then we're gonna write the K expression. We're given molarities again. It says the initial contains CH4 at 0.15. So we're starting with 0.11115, not 5. We don't have any of that or any of that. All right, so which way does the reaction go? It can only go, again, left to right. I can't possibly go the other way because I don't have any of the product yet. So this is not just minus x, though, but minus 2x plus x and plus 3x, stoichiometry. At equilibrium, this is 0.115 minus 2x. This is 0 plus x and 0 plus 3x. And now I'm going to write the K expressions. I'm going to write it over here, actually. So Kc equals the C2H2 times H2 to the third times CH4 squared. All right, what am I given? So now, again, everything's going to be the same up to that point. From there now, we're going to be given different pieces of information, because sometimes we'll be given the K value and asked to find one of the concentrations. These two particular problems, we were given one of the equilibrium concentrations. And this one, we're saying that this one is 0.035. It's also x. Well, that makes that easy then. I don't have to do any subtracting. So 0.035 times 3. This one is 0.105 at equilibrium. And then this one is 0.115 minus 2 times 0.035. And I get 0.045. So now I know my equilibrium concentrations, plug them in, solve for K. Don't forget when you have an exponent. And from there, now we just plug it in. So 0.035 times 0.105 cubed divided by 0.045 squared. And we got 0.020 as the K value. All right, so from here now then, we're just going to vary, again, where we go after that initial step. In this case, we were given an equilibrium concentration and asked to find K. So now these are actually, the answers are in the back. I want you to try these two. So hit pause, give it a try. I'm going to show you the answers. But the answers to these for practice, so these are the ones that are at the end of the example problems in the chapter. I just wrote it down here. That's why I went to grab my paper. The answers to these are actually in Appendix 4 in the back of the book, which is page A55 from the appendix in the back. So appendix page 55, and you can see the answers. This one ends up being 9.4, and this one ends up being 1.1 times 10 to the minus 6. So give those a try and see how you can do on those. All right, so now I want to show you how to predict which direction the reaction proceeds in, even when you're not, or even when you're given different values. So in the first ones, they couldn't go in the direction where you had 0 coming back because you don't have any yet. So none of those could have gone from right to left initially, but some reactions could. And what it depends on is where you are initially versus where you are at equilibrium. So, we have that change that occurs. So we're going to compare where we are initially to where we were supposed to be at equilibrium. So the way we compare whether you're at equilibrium or not is it equal to K? So is what equal to K? Well, we do the same thing. We still do, so here's our reaction. We still do products over the reactants. The coefficients are still becoming exponents, but now we're not at equilibrium. We're at some initial condition. So instead of calling it the equilibrium expression constant or the equilibrium constant, they give it the letter Q and they call it a reaction quotient. But really what we're doing is comparing where are we compared to equilibrium, or are we at equilibrium? And if we're not at equilibrium, which way does the reaction shift to get to equilibrium? So the value of Q relative to K is a measurement of the progress of the reaction towards equilibrium. Do you have too many products, so it shifts to the left, or do you have too many reactants, so it shifts to the right? All right, so at equilibrium, Q equals K though. So again, that's what we're looking for. So I made up this little mnemonic here, but I think the better way to do that is this phrase. And let's try it. All right, so right away we're given the K value. So that's what we're comparing to. If this thing is at equilibrium, the K value is going to be 81.9, or the Q value. So what we're going to do is find the initial. This time we have pressures. So it's the partial pressure of ICl2 squared over the partial pressure of I2 times the pressure of Cl2. ICl2, so we have a reaction mixture. We don't know if it's at equilibrium or not, but the question says, is it at equilibrium? All right, we'll find the Q. So it's 0.355 squared over 0.114, 0.102. 0.355 squared divided by 0.114 divided by 0.102. So for a Q value, I get 10.8. All right, so is this at equilibrium? So right away I can say, well, if it's at equilibrium, it's 89 and it's only at 10. So it is not at equilibrium. But the question is, which way does it shift? Which way does it shift? All right, well, think of it this way. I have products over reactants whenever I'm doing this. And remember, we need to end up at 81.9. So we're either going to be higher than 81.9, which means our number's too high. We need more reactants because we got to divide by a bigger number. Or we need to go up like this case. So you can see Q is less than K. Q is 10.8, K is 81.9. Which way does this thing shift then to get to equilibrium? I need more products to get to K because it's lower. And so this thing is going to shift to the right. So in which direction will it proceed? It's going to proceed to the right. Why? I need more products to get to 81.9 and less reactants. So that's the trick. Let's try it again. Or me again. All right, so this time we have molarities. So we're going to do Kc. So the Kc is 5.85 times 10 to the minus 3. So we need to know what is Q. So we're going to do NO2 squared over N2O4. Plug them in. The reaction contains 0.0255 for NO2. We're going to square that. And 0.0331 for N2O4. So 0.0255 squared divided by 0.0331. and you get 0.0196 for the Q. All right, well, it's definitely not at equilibrium to answer the first question. Oh, no, actually, they didn't even ask if it was at equilibrium. So here's our K value. Q is 0.0196. So Q is time is greater than K. Q is greater than K. So products over reactants, we have too many products this time. It's too high. So this time it's going to shift to the left, which will decrease the value of Q until it gets to K, and then you're at equilibrium. All right, so don't do this one, I think. Yeah, don't do that one. Oh, no, actually, you can do that one. Don't do this one. That's the one I don't like. I knew there was one in here I didn't want you to try. I was just looking at that problem. I was like, oh, you should be able to do that one. But the next one you don't know how to do. I have them in the wrong order. This is actually for tomorrow, practice 14.8. So don't try that one. Try this one. And then on the next page, try that one. So try those two. And then I'll go over the answers in a second. So hit pause again. Try those two. And here are the answers. Okay, so again, we're trying to figure out now what is the equilibrium concentration of CO2. So you're going to see again the repetitiveness of this. I write the reaction, always the same, always write the reaction first. Then we jump right into the ice chart. It says in an equilibrium mixture, the concentration of COF2 is 0.25, and the concentration of CF is 0.118. What is the equilibrium concentration? See, so we're not at the initial conditions this time. So we don't even care what the change is this time, because in an equilibrium mixture, COF2 is 0.255. So now we have the equilibrium concentration. The CF is 0.118, and we don't know this one. All right, so the K expression, as I said, we do the same thing each time. So the K expression is CO2 times CF4 over COF2 squared. We're given the K value. It's 2.0 equals X times 0.118 over 0.255 squared. 0.255 squared times 2 divided by 0.118, and we get 1.10 molar. So at equilibrium, that thing is 1.10 molar. Now, what you could do, now we know this is 1.10 molar. We know the three equilibrium concentrations. We can plug them in and make sure it equals 2.0, but it will. As I said, skip that one. We're going to learn how to do that one tomorrow. And we can finish off with this one. So once again, I'm going to write the equation. Initial change equilibrium. Reaction vessel initially contains only A at a pressure of 255 millimeters of mercury. So we have none of that, none of that. Can only go that way. Now you could do the Q too. Q is equal to the products, 0 times 0 squared over the reactant, 255, and calculate that. Well, it's 0 times 0 times 0 divided by, so the Q is 0. So when we say is Q compared to K, well, K is what we're trying to actually calculate this time. But if we knew it, we could say which way it shifted. But again, we don't have to, because it's never negative. K is never negative. So K is either greater than 1 or less than 1, but never negative. It's not less than 0, it's less than 1. And so it can't be, Q is definitely less than K then. Why is it less than K? Well, it's 0. So it has to go up, which means it goes in this direction. But again, I know it can't go back to the left because I don't have any of that stuff. Minus 2x stoichiometry plus x plus 2x stoichiometry. At equilibrium, 255 minus x, x, and 2x. I'm going to write the Kc expression just to show you that, again, they will all be done the same. Now, this is a Kp this time, not a Kc, because we have pressures. So Kp, remember, you only do gases. They're all gases. Then you do the same thing, but we don't use brackets. So I like to just multiply between like that. All right, what's our information? At equilibrium, partial pressure of A is 55 millimeters. So then what's X? All right, they made it kind of easy there because 200, 55 minus 55. So X is 200, which means this is 400, 2 times X. And now we can get the KP. Now, technically, you're supposed to use atmospheres. But don't concern yourself. If you just plugged it in, that's okay. If you want to go get the absolute correct answer, go for it. Now, the reason you always use atmospheres is, remember, there's no units. And so it's understood that it would be atmospheres. So now I'm taking the values at equilibrium, plugging them into the K expression. Don't forget the coefficients becoming exponents. So now we have 400 squared times 200 divided by 55 squared. And we get 10,570. Okay. All right. Try those homework problems.